Very good. So the literal responsibility of a keynote is to set the theme, to sound the main theme or set the tone. In music, the keynote is the tonic chord, so we're supposed to do that. But the keynote is often abused to be a talk that's completely outside of the mainstream of the community that maybe provokes the community in a new direction. A third alternative is to set the context for the main theme, if you will, in the musical terms, to be a dominant chord. So what I hope to do today is to give the big dominant seventh chord coming from decades of computational science and engineering in the conventional, multiprocessor mode to, say basically that the tank is out of gas and there are some new directions that are needed that I hope will segue directly into Wen Mei's talk and the main pedagogical themes of this meeting. One function of a keynote certainly is to thank the organizer. And in this case, I know that all of us in this room are very grateful for our multidisciplinary, at home in every culture host, Professor Lorena A Barba, who is a graduate of this university in mechanical engineering and is now, of course, a professor at Boston University and a rising star in the GPU business and many of our hopes for migrating high-end applications to practical computers of the future. I'd also like to thank the National Science Foundation and Barry Schneider and the Office of International Activities for their generous support of this meeting. It's thrilling to see these communities coming together at the student level. Look around because you are colleagues that will carry each other's work from across disciplines and across countries forward. It's impossible to be much of a scientist as a solitary person anymore because of the complexity of the problems and the complexity of the hardware and the complexity of all the layers in between. And all of these successful assaults on scientific discovery and engineering design are now in the form of large teams. So developing networks is an important part of earning a PhD nowadays, and in fact of succeeding as a faculty member. This meeting is very satisfying to me because it draws together many of my own worlds. One of my former students, Augustin, who's a faculty member here in computer science, is here, and I learned about, from one of Augustin's students, learned something about Valparaiso in advance because that grandson of mine is now a student at KAUST, if you will. And I have another former colleague from Colombia who's a Chilean who I will see today. And of course I have friends from Colombia and KAUST and NSF and DOE here, and it's just wonderful that this workshop is convening, and I believe that it's an extremely important theme that's being sounded. And as Lorena made the point when talking to NSF, the advent of the GPU and the inexpensive multi-core cluster basically spread supercomputing worldwide very suddenly. You no longer have to have $100 million. In fact, one of the main points of my talk will be that the big gap between petascale and exascale, my talk's about exascale, and that gap, which sounds like a very expensive thing that maybe only 5 people in the world care about, is in fact exactly the same gap as going from the gigascale to the terascale on your desktop. So the problems that every one of you face on your own personal computer in going many core is the missing factor in the going from peta to exa. So we're all working on this together. It doesn't matter how many nodes you have. It matters what you do with the node, and that's why I believe this meeting is really exciting. So if you want to follow up a little bit on the talk, I have a recent paper in Comprendu, which I can send a preprint of, so you can just contact me. I assume we're getting registration lists out of this meeting. Most of my material today comes from the work of others, I should say, from the work of this group here. I don't think a single member of this exascale committee is in the audience except for this lonely guy right there. But the current roadmap, which is probably 100 pages or so, from the International Exascale Software Project is about to appear in the journal IJHPCA. So there's another source to follow up. And of course, the international community, in the form of at least the G8, has started truly coordinated, well, I won't give them that much credit that it's truly coordinated, but they've begun to take coordinated steps towards the gargantuan task of moving billions of dollars or billions of euros or whatever your currency is of software from the PAX MPI world, 20 years of message passing, into emerging architectures. All the countries that are heavily invested at the high end recognize what an expensive proposition this will be and how few people there are that are currently capable of doing it. And so instead of each nation doing it by itself, we're trying to all do it together and not have so much duplication of work, since we don't have that many workers to afford duplication. And this was the first call. There will be further calls, and maybe some of you in this room will be working on this as a direct result of your interests coming out of today. So my questions today are to consider, why go to the exascale. That one's pretty easy, it turns out. And then some hard questions. What will systems 1,000 times faster than today's petascale systems look like? They better not consume 1,000 times the power, because they're already consuming close to 10 megawatts, and that's just not scalable. There's a joke that the computers that forecast global climate have to take into account their own energy needs nowadays. What will the implications of the budgets be for power and for acquisition of this new hardware? And what should we be doing? And I guess I have to confess up front, my talks are mainly directed towards applied mathematicians. How are we going to make use of these complicated architectures that are coming down the road? Well, I can be rather quick on why push to extreme scale. There's a number of well-recognized reasons. Of course, one is that nature is multi-scale and needs high resolution, both space and time. One wants to, expand into a high-fidelity, full physics, full chemistry, full whatever representation of a model. One wants to work in full dimensions. One wants to get artificial boundary conditions or artificial lack of dilution, out of away from clouding the science results by having, big enough domains or enough particles or whatever. One wants to ultimately combine not just one model like an ocean model, but complex models from multiple domains that intersect, that flux boundaries, or even that interpenetrate, like magneto-hydrodynamics, Navier-Stokes plus Maxwell, or ocean, atmosphere, etc. One wants really to solve inverse problems. The forward problem has been the challenge that we've faced up until now. It's gasp over the finish line, getting one run done of some complicated system. But really, the system had a lot of uncertainties in it: initial conditions, boundary conditions, forcing parameters, constitutive parameters. Many of them are amenable to design, and we always want to really invert. Now that we have a desired state, what model could give that state? And that's a much more complicated problem than the forward model. We want to perform optimization or control. We want to quantify uncertainty, which requires multiple runs or single runs of augmented systems with PDFs in them. And these are all, you could say, third paradigm challenges. Third paradigm referring to computational simulation, along with theory, the first paradigm, and experiment, the second one. There's now a fourth paradigm emerging, which is only years old, literally, and is reflected in the fact that the world's data is doubling about every year, and that we're now getting, continual streams from sensors, from satellites, from internet records, high throughput experiments in biology, high resolution experiments in engineering, internationalized sky surveys and so forth. The amount of data that's coming at scientists, it also demands supercomputing. And many of the models that do data mining have not been optimized in a complexity sense like PDE solvers. I mean, we have O of n log n, FFTs, and multigrid and so forth, but the data mining algorithms tend to be quite superlinear in the data size or the number of queries or whatever. And so there are extreme algorithmic challenges in this fourth paradigm of science-enabled data. This is science where you don't have the model. Navier-Stokes, we've had that for 100 years. We believe it's a fairly good model to run through a computer with. But there are many problems in bio, nano, et cetera, where we actually don't have good models to put on exascale systems, but we have exabytes of data, and there's the hope of discovering new science from the data directly through statistical or other models. And so here is yet another motivation for going to extreme scales. Of course, the third paradigm was anticipated by a mathematician writing in a physics journal and a computer scientist, and a physicist writing in a computer journal in the 80s. It's an intrinsically interdisciplinary problem of looking beyond what is accessible by scientific instruments in nature and hooking the computer into that system. And then the fourth paradigm is really very recently articulated, I think, really for the first time in a way that caught the agenda of the National Science Foundation by Jim Gray when he pointed out data is not enough. You have to have all the metadata that goes with the data in order to make intelligent use of data, and this has spawned a brand new focus, and one that I highly recommend any young person maybe consider making their thesis direction. And of course, this recent book, which you can download for free from the Microsoft website, The Fourth Paradigm, is very limited. It talks about medicine and social problems, but it doesn't get anywhere near deeply enough into actually basic science problems, where I think the fourth paradigm also has great sway. So we want to combine the third and fourth paradigms. We want to combine rich data set in the exascale with rich simulation in the exascale, rich referring to not just the forward model, but the inverse problems, the optimization problems, where you actually put in some data that you gathered from microscopes or sensors or whatever, and you try to figure out what the parameters were that could lead to this data. And this, of course, is a mathematically ill-posed problem. You can't just run the forward problem backwards. You have to supplement it with a lot of extra information to remove the indeterminacy, the non-uniqueness of this inversion. And this is a very rapidly developing field of mathematics, because now we finally have computers that are capable of actually doing something reasonable to go along with the theory. Now, I currently work, as Lorena mentioned, in the world's largest oil-producing country, and I like to think of these needs for the exascale. Let's think at them just in the context of one industry, the oil industry. So obviously, we want to resolve reservoirs with lots of mesh points. A mesh point every 25 meters, more around wells, a lot of vertical layers. We want to accommodate physical effects. We don't want to just look at black oil. We want it to have all its multi-fractionated components with different carbon chains and all its phases, and maybe water and other things as well. We want to solve fully 3D. There's no such thing as a 1D oil reservoir, an axisymmetric well, or something. We want to isolate artificial boundary conditions. We want to have enough points to buffer the domain of interest and all of the transit times we care about with, with some, boundary cells where we're not getting, our model contaminated by the unknown. We want to solve inverse problems, as I've mentioned. We have decades of wellhead records. What came out? Well, what was there, and what's left from those records? We want to combine multiple complex models, not just the reservoir production model, but the seismic model, because the properties of the rock change as you actually produce the oil. We want to perform optimization, obviously, to go from 30% recovery to 70% recovery, which many oil people think is actually possible and would, in effect, more than double the world's known reserves by going back and getting all that we left behind the first time and getting it better in the future reservoirs. We want, of course, really we want to get beyond oil and not keep putting so much carbon in the atmosphere. But that's a whole other collection of science problems. Quantify uncertainty. I've referred to that. Improve statistical estimates. This is an example of, I have full permission from Aramco, the world's largest oil company, to show you this slide. They recently have migrated their own primary simulator code from what they call megacell to gigacell, and you can see some of the motivation in these two pockets that were left behind, and in fact unresolved in the previous model. There's a reservoir in Saudi Arabia that takes 5 hours to drive from one end to the other. You need a lot of mesh points. Now, the need for extreme scales goes far beyond just the reservoir problem. Oil companies have lots of reservoirs upstream and lots of customers downstream, and they have choices every single day. Should we produce more of this, weight crude, or should we produce more gas, or you make choices in what you pump in terms of what you get out. And really, there's some huge nonlinear, non-robust optimization problem saying maximize profit while satisfying my own country's needs and getting a good export portfolio. And there's infrastructure like pipelines and ships and people and schedules This is an incredible problem that right now is, of course, just solved intuitively by some managers without a big picture in any computer. These are too complicated for a self-contained, self-consistent theory, like many problems. They're unsuitable to experiment because you can only do it once, like many problems. Engineering heuristics are useful and used, but no longer does one person stay with one reservoir for his or her whole career, and things change rapidly in this business now. So simulation will be an incredibly useful tool for exploring scenarios, and data mining and machine learning will be even more useful tools in the future, because most of the world's problems don't have good models. Navier-Stokes and Maxwell, they are exceptions. Those are those beautiful problems into which we seek recluse when we want to do something useful, but we ignore all the hard problems. Now, the next 9 slides contain some raw output from the applications group of the October 2010 International Exascale Software Project Workshop, which I happened to be the moderator of, and we tried to come up with some other examples besides oil where we could convince our governments to go headlong into exascale funding. And we came up, just because we were a random collection of people in the room, with 19 applications. This is not considered a complete set. It's not considered an independent basis. We don't claim that every math algorithm that will be needed at the exascale is a component of one of these problems here. But it's interesting that 7 of these 9 apps actually were Gordon Bell finalists, and their inventors were in the room. I would say one of the weaknesses of the list is that discrete algorithms are so far underrepresented. And this is not necessarily a statement of priorities from the funders, but these are the applications that are currently driving the algorithmic perspective on the exascale: magnetically confined fusion, molecular dynamics, climate, combustion, radio astronomy. That's actually the most data intensive of these 19 applications. Aerodynamics, fluid dynamics, and heat transfer. Of course, the original problem, that drove us all to computers. Von Neumann's problem was weather prediction. It's nonlinear. You can't do perturbation analysis. You can't do asymptotics. You can't do a lot of things. You have to run to the computer. Neutron transport, nuclear fuel assemblies. The world wants to certify new mixes of fuels for use in commercial power. Normally that's a 20-year process, but maybe the computer can be a time machine and help certify some fuels in time to actually prevent a lot of carbon. High energy density physics, electronic structure. Again, these are major scientific grand challenges. They don't include medical, social, even that many biological grand challenges. There are many others out there. We had each of the proposers of these apps answer various questions. What programming models do they use today? What's the current scaling high watermark? What algorithmic dependencies are under these application names? What software library dependencies? What's the current balance of hardware resources? Is the machine outsized relative to itself in these resources? And what are the theoretical scaling requirements in terms of flops and bytes in both strong and the weak sense? And I know you're very curious to know the answers, and there they are. and I know you can't read them, so you can sort of keep following the report, but I have some summaries here. The almost universal model in terms of programming models for these apps is the bulk synchronous message passing, single program, multiple data, decomposed either by domain or by particle list or some other object. There's one notable exception. The electronic structure codes, perhaps for some accident of powerful personalities, are dominantly not MPI based. They use global arrays, some kind of a global shared memory space. There are other models like Charm++ and distributed objects built on top of active messages and p-threads. So the scientific community has been modestly aggressive in exploring computer science ideas. Some codes have multiple phases. You do a field solve and then you do a particle push. And these are incommensurately distributed. And they're not necessarily compatible, keeping the real estate in common in the two decompositions. So that's a serious challenge, because that means data motion. And data motion, as we all know, and as you've been discussing here undoubtedly already and will for the next 2 weeks, is the dominant problem. These applications are already running hybrid in almost every case. They're already mixing MPI on the outside with some multi-threaded package underneath, and up to 48 cores we found, which was relatively encouraging. And they typically weak scale without any real loss of theoretical efficiency out to the edge of today's machines, 300 cores. Weak scaling is easy for PDE-based codes. I'll make that argument a little bit later in the talk. In terms of memory bandwidth, the majority of the apps are already bandwidth limited with just a couple of processors grazing over the memories available, let alone adding more cores where we don't have bandwidth to use the ones we have already. The flops per byte of storage is generally linear or log linear. That is to say, these algorithms are already fairly optimal in the mathematical complexity sense. In terms of I/O versus computation, I think we were surprised how few of the scientists pushing the exascale are worried about I/O. I think that's actually probably deceptive. But someone like Rich Brower only needs a scalar out after months of computing, so he's not worried about I/O. But actually, to put the gluon field in, you are worried about I/O, right? So yeah, he's nodding. Okay. and we expect checkpointing to become much more intensive and perhaps limiting at the exascale, and users will definitely have to take charge of checkpointing at minimal state points in the code. In terms of communication versus computation, in weak scaling, today's Gordon Bell apps, if you will, have a generally, they've evolved to run on today's machines. That means they have a constant ratio of near-neighbor communication to computation represented by some minimal collection of vertices, cells, particles, et cetera, per processor. If you make that number smaller, you got more skin than body, right? If you think of a 10 by 10 by 10 chunk of a 3D domain, 600 cells are on the boundary, and you only have 1,000 cells. So that's pretty much, you can't get much smaller than that. You're already sort of working at the edge of redundant storage and neighbor communication. So there's some minimum set per process, and then that weak scales fairly much indefinitely, except for the global collective. The logarithm is big when the number is a billion, the log base 2, and that cuts into actual, efficiency. You still have a theoretical gain by using more processors, bigger problem, constant time, but the efficiency is at the edge. In terms of synchronization versus computation, all of these sort of optimized codes require frequent global collectives. This reflects the fact that nature has a lot of reciprocal relations. Mathematically, second order PDEs are solved by Green's functions that have global support. Everything touches everything in a Laplacian. And then there's the stability limitation of an explicit code that says we have to check what's the limiting time step at every point and take consistent time step. Or do we? Well, that's an algorithmic question to ask. But the codes today are very dumb, and they do things in this lockstep way. The core algorithms, no surprise here, I would say. Everybody would expect this. Equilibrium solvers in PDEs, wave solvers in PDEs, FFTs, FMMs, particle push, AMR, sparse and dense linear algebra. The dense, of course, within small regions. If dense is more than 10,000, you're probably solving an integral equation and should do it some other way. But dense linear algebra is very important for high-order methods and multi-component problems and so forth. And ODE integrators. These are the minimum set of today's mostly freely downloadable, mostly Department of Energy developed software that scientists believe they are addicted to and cannot move to the exascale without. And so if you're responsible for one of these packages, you have a job. And probably you all have jobs helping the people who are responsible for these packages. So that's sort of some primary data coming from the exascale workshop perspective. And my remaining plan, and Lorena will have to cut me off at some point. I don't remember when I started. But I wanted to, I think I'll go really fast through, the optimistic, extrapolations from the past and probably not spend much time on looking at one of the kernels that I think has reached the limits of its scalability. In terms of the the MPI world, and then probably try to spend more time looking at the hurdles because you have theses to write. Why do we want to simulate at the exascale, and in what formulations? Maybe PDEs will be less important in the future than particles, for instance. Architectures. What are the hurdles of granularity, cost, power, programmability, system software, reliability in delivering exascale systems, and how can they be surmounted? And the interesting question is, how can algorithms span the complex problems and the hostile architectures? And probably we're going to give up a little bit on the Dijkstra ideal of separation of concerns in computer science. Probably every application person will be looking at the hardware, and every hardware designer will be calling up some application person, and that concept of co-design will get much finer grained than just that level of interaction. From the philosophy of an algorithmicist, myself, applications are given, architectures are given, the market determines them, and algorithms and software must be adapted or created to bridge between the two, and this is more important than ever because Moore's law has become concurrency-based rather than clock-based. Scalability is still important, but there are new memory bandwidth stresses in addition to the old ones, and the greatest challenge is the lack of performance robustness of individual cores at the exascale, and you'll see what I mean in a moment, which can spoil all of our best attempts to do load balancing. Individual processors will not be reliable performers at the exascale, primarily because of power and correctness reasons, because of all the engineering corners that are cut in order to make an exascale machine buildable. So knowledge of algorithmic capabilities can usefully influence the formulations of applications and the actual future design of architectures. And conversely, knowledge of the application and architectural opportunities can give hints to algorithm developers. So we're all in this together. That's why I referred earlier to look around, because you're building your career teams right here in this room. We can look back on a very, very, very satisfying few decades of the Gordon Bell Prize, during which actual delivered performance on real applications has improved by about a factor of 1,000 every 10 years. And this is remarkable. I mean, this didn't happen in the airline industry, right? I mean, this is, if it did, you could go from Melbourne to Chicago in microseconds, right? This year's was not monotonically in the same, in fact, Gordon Bell is not monotonic, it turns out, but, from year to year, progress is made on a variety of formulations, density functional theory, fast multipolar PDEs, variety of applications, a healthy growing number of concurrent processors, both commercial and special purpose machines, and so forth. There's another Gordon Bell Prize, which is price performance, which stagnated about a decade ago because there was nothing beyond the gigahertz processor that was giving double precision, but 2 years ago now, because we're in 2011, a GPU cluster made the next big breakthrough in price performance, and therefore we can claim a similar, almost factor of 1,000,000 in price performance, in addition to peak performance when cost is no object, in the same 20 years. And as Lorena mentioned, many U.S. federal agencies have sought to justify large increases in buying computers and in training computational graduate students by riding what I call this bell curve of really delivered performance on real apps. And this is a sample of the reports that I personally have had the fun of being involved with. So how are problems like these solved at the petascale today? Well, the dominant paradigm, as mentioned earlier from the survey, is iterative methods based on domain decomposition and message passing, where each processor has the same code and a different hunk of the domain. So it's single program, multiple data, bulk synchronous processing, communicating sequential processes, whichever of these acronyms you prefer. They all refer to a stranglehold of a global network with some global communication at some high frequency. And this is where sort of things bottleneck, actually, in many cases. The paradigm is, as I suggest, domain decomposition, where you have a lot of work between data that's stored locally within one memory system and only a lower dimensional amount of work. See here you have a 2D chunk and 1D perimeters. You could have a 3D chunk and 2D perimeters or whatever, but you have the asymptotics in your favor when you look at the communication to computation ratio. And this applies to finite differences, finite elements, control volumes. They all lead to sparse Jacobians. You always do a matrix multiply rather than a matrix solve. So your algorithm is Newton-Krylov-Schwarz, where this basically does it does Daxby's and it delegates a linear solve. This does a linear solve by delegating matrix multiplies and preconditioning steps. The matrix multiplies are very parallelizable because they have this domain decomposed asymptotics of communication to computation subdominancy. And the preconditioners are where the rubber hits the road, because that's where you have to confront the global connectedness of everything in the universe. And in practice, a hierarchical approach where you precondition local interactions well and remote interactions very, very coarsely works reasonably well there too. And these are, I'm not going to go into the math paradigms because you're interested in other things, but here's just sort of a plot of what's happening as a function of time across the machine. You have a local scatter, which, local communication, no computation going on there. You do some burst of local computation. You do a preconditioner sweep, which has no communication, and then you do an inner product, which is globally. This is where your global network is exposed, and then you do a Daxby, and everything resynchronizes at the end of the inner product, no matter how badly the load balance has been in between. And the load balance may be different between the computing and the communicating, of course. And good mesh partitioners like Metis that can have multi-objectives are useful there. And then the whole thing repeats. And how many times it repeats is a function of the math. What's the convergence rate of this method? But you can get a good idea of the computational efficiency by looking at just one of these inner loops and seeing what resources are needed in different phases. And so this is, what the inner loops look like, and the concurrency occurs primarily at the preconditioner sweep. And this is, of course, a core algorithm in PETSI and in many PDE solvers. Now, what will general purpose exascale systems look like to host an algorithm like this? Many paths beyond today's CMOS silicon-based logic, but probably none of them by 2018, when we want the exascale to occur. We had gigaflops in 1988, teraflops in 1998, petaflops in 2008. Everybody wants a continued factor of 1,000 in a decade. By 2018, we won't have new, computer engineering at the device level then. We might have new memory coming along, but recently carbon nanotube memory has taken some hits, and I'm not expecting it. There are two paths. One of them IBM can do by itself because it's a vertically integrated company that has 3 petascale architectures: the blue gene, the power, and the cell. And some interesting merger of the 3 will happen no matter what the rest of the world does. All others will be some GPU-based spin-off. And for PDE-based scientific codes, the programming model will still be message passing, I guarantee it, because of the large code base. We can't rewrite the codes in 10 years. But it will have to be adapted to multi-core processors beneath the MPI interface. And the most important phrase on this slide is the last one from the mathematical point of view. We have to move to less synchronous algorithmic development. One of the paths towards the exascale, which was designed by Pete Beckman and colleagues at Oregon, is the following. And I won't go through each of these lines in detail, but I'll point out that the computational power, the top line, the system peak, has to go up by a factor of 1,000, while the power, the electricity, goes up only by a factor of 3. Now that is a tough engineering problem, but that factor of 3 is a severe upper limit because that puts the machine at 20 megawatts. A village of 14,000 people uses 20 megawatts. So you can have 14,000 people living, breathing, driving cars, whatever, or you can have an exascale computer. You can't have 1,000 times that resources going in an exascale computer competing with the world's population need for energy. The system memory can only go up by a factor of about 100. So we're taking a factor of 300 in power efficiency hit. We're taking a factor of 10 in bytes per flops hit. And a similar hit in memory bandwidth. So memory bandwidth is already the limiting resource, and there's no way to get to exascale without it becoming a much, much more severely limited resource. This is all very unfortunate, but these are non-negotiable upper boundary conditions. You'll see where they come from. Suppose that memory bandwidth alone was eating up the entire electrical power budget. Here's your electrical power budget, 20 megawatts. And these are the cost of moving bytes per flop, I mean, in other words, scaled to 10 to the 18th flops, for different generations of memory excellence, from 30 picojoules per bit, which would be a fairly non-aggressive design, to some things where the hardware designers may be able to give us more. And so for each advance in memory technology, from more or less sort of extrapolating today's to some really successful far out designs, we might have as many as like half a byte per flop, which violates the Amdahl case rule in terms of keeping your bandwidth proportional to your ability to do a flop. Yep. I don't know, actually. I just this chart came from a report that Rick Stevens and Andy White are writing, and I just got a draft of it yesterday. I've been bugging Rick, and so I'm sort of quoting the chart without knowing all the data behind it. But we can answer the question at lunch or whatever. Thank you. And this other is also from the Stevens-White report, and this shows that if you're limited to $200 million for your exascale computer, and I think no national laboratory is going to get more than $200 million for a computer, and if you spend half of it on memory, which is a reasonable architectural design, then for an exascale computer, you might only have at most 100 petabytes of memory. So again, the Amdahl case rule is being violated. You have a lot more flops available than you can store things coming in or out of those flops. Of course, everybody in this room knows this slide. That's why you're here. You know that power consumption goes like the cube of the frequency. So taking a gigahertz processor to a 4 gigahertz processor, that's a 64-fold increase in power required, whereas taking a single core to 4 cores at the same clock frequency is only a 4-fold increase, and so we need, of course, to go multi-core. The implications of these architectural and cost limits are, expanding the number of nodes to 10 to the 6th. We're almost there today. That's not a serious threat. We know how to do well load balanced algorithms at 1 million nodes. If the nodes give a reliable, if they all perform the same way, for their equal balanced load. The real challenge is expanding the number of cores on a node from 1 to 10 to the 3rd. And this must be done while memory bandwidth and memory bandwidth per node expand by at best 10-fold or less. It is already about 10 to the 3rd slower to retrieve an operand from main DRAM than to perform an arithmetic operation, so this will get worse by a factor of 10. So almost all operands have to come from registers or upper cache, and there's an incredible algorithmic constraint for a method like Krylov, where you have to drag the Jacobian through cache every iteration. There's a draconian reduction in power per flop and per byte that will make computing and copying much less reliable. The voltage difference between 0 and 1 will be reduced almost to the noise level. So statistics may have to enter into doing floating point operations. Circuit elements will be smaller and subject to greater physical noise per signal. We can no longer compute at Los Alamos because there's more cosmic radiation there than down at sea level. And power will have to be cycled on and off, or clocks slowed and speeded based on compute schedules and based on cooling capacity. When you put 20 megawatts into a square meter or something, things start melting, and the actual at certain times in the computation, a chip may say, "Sorry, I got to stop computing for a minute. I'm going to melt." That's an example of the kind of lack of reliability that we will have. So there are many sources of non-uniformity that haunt a single program, multiple data, bulk synchronous, communicating sequential processes, load balanced computation. From the system side, there are always manufacturing non-uniformities, but now there'll be dynamic power management, soft errors, errors that don't bring the computation to a halt because they don't segfault, but they might give you the wrong answer. Hard component failures, operating system jitter, software mediated resiliency, That is to say, the software does some compensation for the errors, and that takes time. Of course, there's always TLB cache performance variations, network contention, and so forth. There are new sources, there are the usual sources of non-uniformity that we put into our algorithms because we want our algorithms to be optimal. You know, we want to have adaptive high-order methods, adaptive gridding, adaptive physics, and so forth. Effects are similar at a synchronization point, whether your non-uniformity came from the first batch or the second batch. In the past, we've never worried about the first batch. We've spent a lot of time worrying at the second batch, and we've been very successful. And the bad news is the first batch is going to throw all that out the window, but the good news is we have to solve the first batch so the second batch can go along with the same solution. If we have to relax synchrony, then we can relax synchrony and you know, worry less about load balance at the algorithmic level as well. And this will improve programmability. So I put in a tombstone for the end of the MPI era, and it's basically because of the lack of the ability to load balance that load balance is not enough to come up with a well-synchronized code. Now, there are many moans coming from the application developers based on this outlook. So what are we talking about at the exascale? We're talking about a mega node, gigahertz, kilocore, right? Mega node, 10 to the 6th nodes, gigahertz, 10 to the 9th operations per second, kilocore, 10 to the 3rd cores per node. Memory bandwidth is already limiting at today's low core count, and it's only getting worse. Processors are cheap relative to memory. They're very small in chip area and very low in power. So there's no harm in having them in excess most of the time. As an engineering optimization, if you have something that costs nothing and takes up no space, and you can occasionally use it all, then you should put a lot of it in. But you shouldn't measure your efficiency by all that excess that you put in to be occasionally used. The efficiency has to be measured by the power and real estate expensive thing, which is the use of memory. And there is an opportunity for combining today's individually high capability simulations into complex ones. That's the whole government motivation for the exascale. But merging the two data structures is not going to be easy. That's actually what the exascale is not going to be good at, is having a lot of memory to mesh things together. So there's a real disconnect between the way the exascale program is being sold to the government in terms of modeling our complex world and what it may actually be good at. Of course, the first thing it will be good at is QCD, and whether it will be good at anything else, maybe Rich doesn't care, but we'll get some use out of it. But so some chief issues identified by the applications groups are not in any particular order: I/O, fault tolerance, reproducibility of computations, and programming models and algorithms. I actually think the last one is the most interesting, so we'll get to that. For some important apps, I/O is a likely bottleneck. This could be either for input or for output, or for checkpointing, or for some combination of them. But I/O is beyond the scope of this algorithmicist's talk. Fault tolerance. Users will recognize their own need to do checkpointing because it's too wasteful of I/O and processing cycles to have the operating system detect errors and dump everything. Different types of faults may be handled in different ways. You may decide that a bad pixel in your visualization movie should not stop the computation, whereas a seg fault probably should. And strategic minimal working set checkpoints can be orchestrated by the application developers and users to help with this problem. Reproducibility is a hard one to swallow, especially if you're a computer scientist. Exascale systems will not be reproducible in terms of you give them the same input, they will not give you the same output. It's guaranteed. We don't have that today, by the way, because if you add up floating point numbers in a different order, because the messages came in across a network in a different order, you get different sums because of floating point rounding. But the new emphasis at the exascale with the low power, low voltage switching transistors is that lack of reproducibility may emerge for many other hardware-based reasons, and we may have to take account in the algorithms of detecting these soft errors and either saying mathematically we know that their effects are bounded. For instance, it might be some parabolic problem with a rapidly decaying Green's function. We say, yeah, there might have been an error, 10 mesh cells away, 10 iterations ago, but I don't care because it couldn't be bad enough to affect, the first 5 digits of many errors are tolerable. And computer scientists aren't used to thinking this way because they're used to lawsuits for, X-ray machines that went wrong or missiles that launched at the wrong time or whatever. But in scientific computing, we're gonna basically be tolerating, millions of errors per second if we do, quintillions of operations per second. Application developers are tolerant of irreproducibility actually already because we're moving into an era of statistics-based uncertainty quantification. The data wasn't reliable. Why should the computer be? I mean, we can still get some numbers out, right? And we have to balance in a well-orchestrated mathematical way all the sources of uncertainty in order to arrive at, good science per dollar. The programming model is perhaps the most interesting and gripping thing. It cuts across the whole community. And prior to possessing exascale hardware, you are at the vanguard of the programming model issue right here in this room on many core and heterogeneous nodes. Attention to locality and reuse is valuable at all scales, valuable on your Mac Air, as well as at the Tianhe one in Shenzhen, the world's #1 machine right now. New algorithms and new data structures can be explored under the guaranteed assumption that flops are cheap and moving data is intolerably expensive. Bandwidth pressure can be reduced, and this is an important topic for numerical analysts, by considering mixed precision algorithms. If you go from double to single, you have twice the bandwidth and twice the storage per word. And this may be actually, you might be able to do 90% of your computing in single precision and still preserve double precision accuracy with maybe a small extra cost, as in iterative correction in classical linear algebra. Relaxation of synchrony, if we could do that, if we could move beyond some physical causality or maybe some artifactual causality that we build into our PDE models, that could relieve pressure on load balance. So, right now we have either shared memory or distributed memory or hybrid or maybe hierarchical hybrid, where the coherence of the local memory is not, where there's sort of telescoping domains of coherence across the machine. And the programming model probably should be general enough to distinguish between replicated pieces of data at these levels and how broad their domain of coherence has to be. Because we need that efficiency. It complexifies the model, but it simplifies the architecture and makes the machine affordable. It's by now a well-demonstrated fact at small but encouraging levels that hybrid programming really does work. You can beat message passing with a hybrid. This is a weak scaling result of a kernel FFT from Berkeley. Here is a full app from Demkovich at Texas showing the deteriorating scaling with the wall clock time curving up at high granularity with pure message passing model, but when multi-core processing was exploited, that reversal of efficiency was deferred for a decade or so of processor cores. So, we definitely have light at the end of the tunnel, or at least partway through the tunnel of the hybrid model, the MPI plus X model. But hybrid programming models are probably not enough. In other words, I'm not assuming that we can stay with bulk synchronous and just hybridize. I don't think that's enough for the exascale. Even perfect knowledge of resources and perfect load balancers will not rescue a billion thread SPMD implementations because the cost of rebalancing is frequently too large and the penalty for not rebalancing is fatal. I think the evolution of parallel programming models has to break the synchrony stronghold that we artifactually put into all of our apps today. For instance, in that Newton-Krylov-Schwarz kernel for most PDEs and PETSI's workhorse algorithm that I showed earlier, there's this critical path which consists of solving a linear equation to get the state variable update, bounding that step with some robustification algorithm in Newton's method, and then doing the update. Those are the key steps that take the state from one step to the next. But we insert into those lots of things artifactually, like working on computing a new Jacobian, or refactoring the preconditioner, doing convergence testing, adapting algorithmic parameters, doing I/O or data compression, doing visualization or data mining, we often embed those into that critical path. This is work that can be done at greater leisure, maybe somewhere else, when cycles are available with some work-stealing queue, if we programmed our scientific apps like we programmed our operating systems, with different tasks, with different priorities, and the priorities fire when their operands are ready. So these are actually not new ideas to computer science. They're only new ideas to scientific computing, and they have to be brought back in because now the architecture is limiting. So adaptation to asynchronous programming styles, take fuller advantage of asynchronous algorithms. We need to develop greater expressiveness, creating separate threads for logically separate tasks whose priority is a function, a time-varying function of algorithmic state, joining priority threads in a directed acyclic graph. When everything's available, then the next node fires, and so forth. Jack Dongarra has rewritten a lot of scale-a-pack in terms of DAGs, and we need to do that in a lot more scientific computing. And there are some, early steps in such programming models from IBM and elsewhere. And there are historical attempts to make algorithms less synchronous that failed because they weren't needed, and synchronous was the same cost and better, but no longer will it be the same cost. Next year, Brown has joined several other places in the US where NSF is hosting math institutes, and one of the very first workshops that they will do at this new workshop is a synchronization reducing algorithms workshop to try to get this very much in the view of mathematicians. Well, I'm nearly at my hour, so I think I'll just show a movie for the rest of the talk so you can see what the headlines would have been. And let's see, this one is important. Almost every drawback of the exascale is simply an exaggeration of an inefficiency that we face today. So poor scaling of collectives, poor performance of sparse matrix vector, poor scaling of coarse grids, lack of reproducibility due to floating point non-commutativity, difficulty of understanding and controlling the vertical memory transfers. We already are working on these problems. They only get worse, but they're not new problems at the exascale. The path for scaling up applications has three factors. We can weak scale up to the end of distributed memory. If we only get 10-fold more memory at the exascale, then we can only weak scale by one more factor of 10. That means we have to strong scale the rest of the way. So strong scaling to use the cores per fixed memory unit. And those are two factors. And then the third factor is to scale the workflow. Maybe we actually won't solve bigger problems or solve fixed problems faster. Maybe we'll solve more problems at once. And when you come to uncertainty quantification, this is actually a very relevant direction, and one that is scientifically very legitimized. It's not a consolation prize for an exascale machine to break it up in, adaptively at different phases to a bunch of petascale machines and scale the workflow. The process of migrating from peta to exa is staged. Any of these three are good candidates for your PhD thesis, valuable by themselves. The question is, will they all work together? If three different people solve these three problems, can we just multiply them together? I think we can, actually. This is the job. This is the software that goes into a petascale computation today. A lot of the software is developed by the physicist or the mathematician, the model-related stuff. A lot of it is related to the development phase when you're actually, working on the code. And then a lot of it is related to the production phase when some physicist who doesn't necessarily understand the code is using the code. Almost all of this software is guaranteed not to be supplied by the vendor. Maybe a little bit, maybe the compiler within a node or something. But normally this software is supplied by the US Department of Energy and increasingly by international collaborators. In fact, PETSI probably has about 6 nations contributing to it right now. And when you make something open, guess what? The world debugs it for you and the world adds features for you. And the whole world is now networked. And so we do expect that the whole world will contribute. And we won't get there without that. That's what I care about, that one little bullet. But hopefully you care about other bullets. So these are some priority research directions: advanced mathematical methods for scientific understanding and exascale simulations, including UQ optimization, analysis, visualization, validation, verification. Exascale algorithms that expose and exploit multiple levels of parallelism, support for multiphysics, multi-scale methods, exascale methods for constructing and adapting discrete objects, the neglected frontier of algorithms, because algorithms that deal with unpredictable dynamic workloads have few flops. There's a lot of integer work, a lot of pruning and reordering and partitioning and so forth. Mixed precision arithmetic is a real important frontier for numerical analysts to give their attention to reformulate algorithms to find the corrections, the lower bits, rather than to work with the full resolution of the problem. A progressive byproduct. The consolation prize for all this bad news is that writers of algorithms have been waiting for a long time for freedom to adapt the mesh, freedom to do everything you're supposed to do from the numerical analysis point of view, but has been hard to do in a bulk synchronous computation. The wrong reward is to actually measure the flops. I think we understand that in this room. People they'll complain you don't get much peak for your exascale system, but in fact you're peaking the memory use, peaking the memory bandwidth use, you're using your system well. The right problem is the one that provides the requisite accuracy with the requisite confidence at some combination of lowest energy and shortest execution time, not the one that fires every transistor every cycle. And so some summary themes. I think I have covered these, and I'm out of time. So again, we've looked at some past progress and how it may not extrapolate. We've peeked at some motivating applications. We've looked generically at a kernel from a PDE-based code. We've looked at some hurdles and opportunities for PDE-based simulation codes. And I want to conclude with a quote. We choose to do these things not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we are willing to accept, one that we are unwilling to postpone, and one that we intend to win. These were the words that started the Apollo moon program. That actually finished in 7 years. Well, we have 8 years. Well, we have 7 years now till 2018. Yeah. So I think actually the exascale problem is much harder than the moon problem, much harder, and will take many more people, and it will have to be fully international. But I think all the right reasons are here. We do this not because exascale is some magic number, but we do it because we have to solve all these problems anyway, and the exascale is a way of getting these problems organized and funded and so forth. But really, the joy is in the journey for this particular problem. And of course, we shouldn't worry because we have petascale systems to approach the exascale with. These are very low power systems, actually. A couple of hamburgers a day, not a nuclear power plant of 20 megawatts. They only weigh 3 pounds. They're not very reliable, but when you put them together, you can make really good judgments. So let's start talking about the zetascale. That's it. Thank you.
Would you like to entertain a couple of questions before we go to coffee break?
Sure, and I'll be around all day. So Rich, of course, has. Yeah.
I understand. Great talk.
Thank you.
I understand that integer arithmetic is more power conserving than floating point in general. Isn't that correct?
Good. That's very interesting if that's true. It could well be true because in floating point you have to do all these shifts and checks and everything.
So,
Yeah.
anyways, suppose this is
Yeah.
true.
That's
This is true.
that's a really good frontier.
Yeah, okay. So, along with your, first of all, I would stop talking about flops.
Right.
Totally.
Yeah.
The other thing is, along with your multi-precision, I can imagine, at least in the algorithms I know, converting a gigantic amount of it to integer arithmetic and ending up with floating point precision.
That is a really cool idea.
And I could rewrite my entire thing in almost 99% integer arithmetic. And if that would save power, and of course the integers are shorter,
Yeah.
therefore it saves communication. But I'm afraid there's a little features of this already in GP by accident because it was never intended as a floating point machine, right? But I'm afraid that the processor designers may not be thinking about this axis enough.
I
And I think it's worth thinking
Yeah.
about it if I am correct.
Yeah.
I think they have huge scale points. That's why we got away from doing that. They used to do that, and then you'll have problems where across the domain you'll have tremendous scale variation.
That's an algorithmic question. I know how to deal with that.
Okay.
This is applied math. No, for solvers.
Okay, so,
Okay?
yeah.
So if you can do it for solvers, you can do it for
Yeah,
a lot.
so-
Remember that cores are free.
Yeah.
So it would be nothing to provide the entire set of integer cores along with all the floating point cores and give you this option. So
I think Rich just entered a really good point into the discussion and is going into the next version of this talk, but let me repeat it. He said, can't we do a lot of flops with integers? And in fact, David Shaw's new machine, the Anton machine, of which there are 14 copies doing personalized medicine right now, they're in the, they're not at the petascale, but they're in the many terascale, is an integer machine.
Now what I want is a machine that has both.
Yeah.
So that we throw that into the mix of mixed precision.
Mm-hmm.
It's also mixed format.
That's right. That's a deep point. And I haven't thought about it in terms of how it could influence the algorithms that I think mostly about. But yeah. Yeah. Okay.
Do you think part of the memory wall problem is that the short-sighted way that people design memory for the traditional processor, where low latency is your biggest concern, and therefore they don't make the buses nearly as wide as they could be because they can't get that kind of random access?
That's another very good point. Let's see. At the supercomputing meeting, there was a panel on Friday where the people who have the DARPA advanced architecture, I think there are 5 groups. One of them is headed by Carnegie Mellon, one of them is NVIDIA, and so forth. And they all gave a report. And one of the reports talked about the wastefulness of RAS-CAS memory, where you fire up an entire row just so you can sample it at one column. And there is, in fact, possibly a lot of more power-efficient ways of retrieving and storing data that could help with this. Now, when I talk about going from 30 picojoules per bit down to 4 picojoules per bit of a transfer, I don't know whether some of those advanced ideas are factored in already. But that's another very creative idea, since we do have some architects in the room. One problem with, architecture is the law of scale that you have to do in order to make something cost effective. Bill Dowley of NVIDIA said that if you can tell me a feature of my chip that will only make it cost 10% more, but will make it sell in the entire scientific market, like some scratch pad memory, then we'll put it in. But it can only cost 10% more and has to sell huge volumes. But you're talking about radical changes here, like a full complement of integers that nobody knows if they can use them yet, or a different way of accessing memory. These are things that will be hard to explore in a cost-effective way quickly. But yeah, well,
as you say, cores are cheap.
in mass fabrication. Yeah. But getting a chip to design, getting a chip to fab is expensive. You risk the whole company on a chip, just like Boeing risks the whole company on every plane. Yeah,
in fact, that's the real problem, is this whole design, because we've got to do with commodity parts.
Mm-hmm. Yeah. Okay. Well, it's an honor to be part of your workshop and see you around this week.